Welcome back, everybody. This is going to be part 2 of 6 in my lecture series on exponentials and logarithms. In the last video, we took a look at a couple of properties of exponential functions and what they look like algebraically. But in this video, we're going to look at what they look like graphically. Let's get started. With these guys, I think there's no better way than to just try a couple of examples. Remember from the last video that I know the point 0, 1 is on this graph, and the point 1, base, or 4, is on the graph. So let me start on my coordinate axes by plotting those points. And here I'm going to count by 2's on my y-axis. So I will have 0, 1, and 1, 4. Now, remember that I said in the last video, when the base is bigger than 1, that's this case, we're modeling exponential growth. The shape of this graph is going to look almost like an airplane taking off. Like that, where we get really close to 0, but we never actually touch it here on the left side. And here, again, this is the point 0, 1 and 1, 4. In the next problem, you'll notice that my base is between 0 and 1. So this is what we call an exponential decay model. So I know that 0, 1 is on the graph. I also know that 1, the base is on the graph. So let's plot those points on my coordinate axes. Here is 0, 1. Here is 1, 1/2. With exponential decay models, it looks like an airplane coming in for a landing. Like this. Sort of a fun thing to think about here, and I would challenge you to try and work this out on your own. Why is it that the decay models almost look like a reflection of the growth models across the y-axis? That's sort of a challenging problem, and I'd encourage you to think about it and reach out to me if you think you have an answer. Now, just like all of our other functions we've learned how to graph, we can also use transformations on these guys. So let's try doing that to sketch the graph of this guy. Let me start by drawing a coordinate axis. So I notice, first of all, that I have a horizontal transformation here, or translation here, right? I need a shift. First, I need to shift left 1 unit. And then I have a vertical translation also. I need to shift down 1 unit. In my parent function here, the parent function would be y equals 2 to the x. So this guy I know has 0, 1 on it and 1, 2. So let me sketch that. And again, my base is bigger than 1, so this is going to be exponential growth like this. I'm going to move left 1 unit. So here's 0, 1. That's going to move to minus 1, 1. 2, 1 is going to, 1, 2 is going to move left 1 to 0, 2. Then they're going to move up 1 to their final position. Negative 1, 1 is going to go to negative 1, 2. And then 0, 2 is going to go to its final position, 0, 3. And then I can sketch my graph. As you can see, we can use transformations to sketch the graph of more complicated looking exponentials. For this problem, you'll notice an interesting number showing up here. This E is called Euler's constant. E for Euler. And E is an irrational number, just like pi is, and it's about 2.71828 blah, 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 blah. There's other numbers after this, and it goes on forever without repeating a pattern. This number we're going to talk in more detail about in some of the future videos in this series. For now, just think of this as about 2.7. See if you can pause the video here and sketch the graph using transformations. This is the graph that I found. Feel free to pause the video here to take a look over my work. In this video, we saw how to sketch the graph of exponential functions. In the next couple of videos, we're going to do the same process but with logarithmic functions. Catch y'all in the next one.